Okay, everyone. Hope you're all doing well. Can you hear me? Okay, good. I have a headset on because, again, I'm in the back bedroom and my French bulldog's in here and he is very, very loud. So it's constantly licking or farting or whatever combination of things. All right, so we're going to start lecturing today on chapter 2. The lecture is formally scheduled to go to like 8:40. We probably very rarely will stay that late. We'll just, move efficiently. Obviously, if you guys need additional help or problems, you can always tell me to slow down or ask for whatever you need or stay after. Okay. So let's share our screen here. Do note that we are not, well, we don't meet on Mondays anyway because of that being our quote unquote lab period, but it is Martin Luther King. So that's sort of scheduled in. Make sure you get the syllabus verified by Sunday evening, even though you don't have class on Monday. Get that done ideally before then, but by midnight. And then also get into mastering chemistry, working through chapter 1. I know I've had a couple emails from people saying that mastering chemistry has been giving them a hard time. Make sure that you enable pop-ups. So you might want to shift which browser you're using. I know that mastering chemistry is not happy. It's not happy in Safari. I mean, sometimes you can run it in there, but it definitely prefers Chrome or Firefox. So you may have to shift your browser. Okay, so chapter 2, this foundational chapter, is talking about measurements and problem solving. So we're going to be doing a bunch of stuff with numbers, getting our foundation for units, numbers, prefixes, all that sort of stuff. One thing that they kind of throw out there, like in the first slide, and then don't revisit till later, is this idea of uncertainty in measured numbers. So in science, different than math, you're using, pure mathematics, you're using numbers. In science, we're measuring values. So there's a certain level of precision to those numbers. The more precise you are, the more significant figures you have. So do know that every time you have a measured value, there is a certain level of uncertainty to that value. So when I look at this says average global temperatures have risen by 0.6 degrees Celsius. This slide is outdated. It's definitely bigger than that now. But this last digit or the rightmost digit is always an estimated value. So it could be as high as 0.7 or as low as 0.5. It wouldn't be 1 degree. That would be out of the range of uncertainty. But there's this plus or minus a single decimal place. If this number had more decimal places, the first part of it would be certain. It'd be that last value again that's estimated. So scientific notation, and all sciences use this, but chemistry especially, because we're dealing with really, really big numbers, like how many atoms are in the oxygen in the room you're sitting in. And then we're also using really, really small numbers, like what's the distance between 2 carbon atoms in a diamond. So it can get kind of cumbersome to write really large and really small numbers. So we need a more consolidated way to do that. And the way we do that is with scientific notation. And your scientific notation is always going to have 2 components. It's going to have a decimal part in the beginning, and then it'll have a secondary exponent. The decimal part has to lie somewhere between 1 and 10. Now, really it's 1 and like 9.99999, because if it was a value of 10, we would move the decimal over to get to a value of 1. The exponent, it's always going to be times 10 to the, and then there's going to be some sort of value in the upper right hand corner. The numerical value is telling you how much bigger or smaller the number is, pretty much how many decimal places you need to move. And I'll show you guys this in a second. And then the sign, in this case, it's a negative. The sign tells you whether you're describing a big or a small number. So a negative exponent is talking about a tiny number. So 1.2 times 10 to the negative 10th is a small, small number. If this had a positive, or if there just wasn't a negative sign here and you inferred that it's positive, that would be talking about a large number. So couple things to note. When dealing with very large and very small numbers, we can use this exponent thing. 10 to the power of 0 is actually equal to 1. 10 to the power of 1, whatever that exponent is how many zeros you'll have in your final answer. So 10 to the power of 1 is 10, or 1 times 10. 10 to the power of 2 will have 2 zeros, right? So 100, 10 to the power of 3, 3 zeros, 1,000. 10 to the negative 1, instead of taking that one value and multiplying it by however many tens you have, here it was 2 tens, here it was 3 tens, you're going to divide by however many tens you have. So it's 1 divided by 10, which would be 0.1 or a tenth. 10 to the negative 2 is 1 divided by 10 times 10, which would be 1 divided by 100, or 100th place, and so on and so on. So to convert a number into scientific notation, the first thing you want to do is find the decimal component, then work and find the exponent. The way you find the exponent is you take where your decimal is in the original number, you move it over to get to your decimal place, you figure out how many times you have to hop. I think it's just easier to show an example. So let's say we have 42 million. And FYI, my handwriting is bad already, and it is much more difficult on this like tablet that I have from 1995. Thank you, AV Tech. So let me know if you need any clarity on what's happening here. But 42 million. So this is a large number. The decimal is living right here. It's not drawn in there, but that would be where the decimal place is. We want to represent this in scientific notation. So the first thing is to find a number that can be that represents this between 1 and 10. So I would move the decimal from there. I would move it right here. Okay, so 4.2. 4.2 would be the decimal part of it. Why don't I put the decimal here? Because that would make it 0.42. That's less than 1. Okay, why don't I put the decimal here? Because that would make the number 42, that's greater than 10. There's only one place that decimal can move that'll give you a number between 1 and 10. So for us, it's 4.2. Now I can't take 42 million and represent it as just 4.2. We've lost like how big the number is. So we need to include the size or the magnitude of the number, and that's where the exponent comes in. So we're gonna go times 10 to the, that's always the same. The exponent is gonna change though. So the exponent represents how many hops you had to take to get to your new decimal place. So we started here and we had to hop 1, 2, 3, 4, 5, 6, 7. 7 hops, okay? So I'm gonna put an exponent of 7. Now, as far as putting it as a positive or a negative number, some teachers will teach it, hey, if you move to the left, it's going to be a positive. If you move to the right, it's going to be negative. But if you're going in the opposite direction, when you're trying to go from scientific notation back to the numerical value, you move in the opposite direction. So I think that can be a little confusing. Instead, I just like to think conceptually. Am I trying to represent a big or a small number? If the number I'm looking at is a big number, keep it positive. If the number I'm trying to represent is a small number or a decimal, tiny number, we'll use a negative value for it. So here we can just keep this positive. So this thing here is going to be 4.2 times 10 to the negative 7, or sorry, 4.2 times 10 to the positive 7. This initial number had what? 1, 2, 3, 4, 5, 6, 7, 8 characters. This number has 1, 2, 3, 4, 5, 6, 7. So it's slightly shorter to write it that way. Let's do a number in the other direction. So let's say I have 0.00000, 1, 2, 3, 4, 5, 6. Let's do 7 zeros and put an 8 and a 5. So this is a tiny number. We're going to follow similar system. My decimal is here. It's a little easier to see. Here you have to infer that it's at the end. I want to move my decimal to the only position that will get me a value between 1 and 10. So that's going to be nestled between the 8 and the 5. If I put the decimal in front of the 8, we're at 0.85, too small. If I put the decimal after the 5, 85 too big. So it's got to be that 8.5. 8.5. Now we're going to go times 10 to the, that doesn't change. And then we have to add our exponent. So let's count up our hops. To get from here to our new position between the 8 and the 5, we have to go 1, 2, 3, 4, 5, 6, 7, 8. 8 hops. Okay, so the magnitude of my exponent is going to be 8. And then you want to ask yourself, am I representing a big or a small number? This is a small number. So I need to add a negative symbol to it. 8.5 times 10 to the negative 8th, because we're looking at a teeny tiny number. Anytime you change the appearance of the initial number, you need to preserve that magnitude with the exponent. So going back to the slides. Oh, hello. Here are 2 examples. This number here is not really a number I would write in scientific notation, because if you notice, the first number has 4 characters. This one has 4, 5, 6, 7, 8 characters with a decimal, almost 9 characters. This is more cumbersome to write, but they're just using it as an example. So if we have 5,983 and we want to write it as a, or we want to write it in scientific notation, you find the starting decimal place. You figure out what your decimal is going to be, the decimal part, the beginning part, which is between 1 and 10. So we'll nestle it between the 5 and the 9. So it'll be 5.983. It's not enough just to write the decimal part. You have to then add the exponent. In this case, we hop 3 hops, so it gets a magnitude of 3. And this initial number is greater than 1, right? Or greater than, greater than 1. So anything greater than 1, we're going to classify as a larger number. So it'll get a positive value. This thing over here, the decimal is sitting there. We want to move the decimal so that we get a number between 1 and 10. So 3.4, the new decimal position will sit here. And we have to count up our hops. So hops are 1, 2, 3, 4 hops. All right, so our exponent is going to get a value of 4. And this initial number is tiny. So tiny numbers will get a negative value, or any number that's less than 1 will get a negative value. All right, how are you guys with that? If your screen's on, you can just give me a heads up or a thumbs up. I'm going to give you guys an example or 2 to work through on your own. So I want you to write all these numbers in scientific notation. Okay, so that's 48, 0.0000035 and 601200000. Okay, so take those 3 numbers and write them in scientific notation, even if it feels kind of ridiculous to write it in scientific notation. Try it out. And we'll come back together as a class in about 2 minutes. Okay, so for 48, I probably wouldn't write that in scientific notation, but let's do it anyway. So the decimal is currently here. I want to move it to this position here. So we're going to go one hop to get me to this 4.8. In order to move in that direction, I need to take a single hop, and it's a larger number, larger than 1. So 4.8 times 10 to the 1 power. This one here, the decimal is sitting right there. We want to move it all the way over here. So our decimal component will be 3.5. 1, 2, 3, 4, 5, 6 hops. So it's times 10 to the 6th. And I have to add a negative value because this is a small number, a number less than 1. Here we've got a large value where the decimal's sitting there. We want to move it between the 6 and the 0. So my decimal component of this scientific notation is going to be 6.012. You always use any of the significant figure values, and we will talk about significant figures a little bit later. So don't get too freaked out if you're like, why did we use some of those numbers and not any of the zeros? Times 10 to the 3, 6, 9 hops. And that's going to be positive. Okay, any questions with that? Going from the number to the scientific notation. Okay, so let's try going the other direction. Just we'll do 1 or 2 of them. Let's say that I give you something in scientific notation and I want you to expand it out. So we'll do one together, 8.1 times 10 to the 6th. So I write the decimal, 8.1. Is this, you got to ask yourself, is this talking about a big or a small number? In this case, we're going to be trying to make a big number. So again, some teachers say, well, when you're going in that direction, you want to move it to the right. I just say move the decimal in the direction that's going to make it a big number. If I move off this way, my number is going to get smaller. If I move this way, my number gets bigger. So I need to move it to the right or in the direction that makes it bigger by 6 hops. So we've got 1, 2, 3, 4, 5, 6. The new decimal is going to sit right here. Now, we can't just leave the number like this. We have to fill those empty hops in with zeros, and the zeros will give you the magnitude or how large the number is. So this gets a 0, so does this, 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 and this. All right, so 8.1 times 10 to the 6 is the same thing as 8,100,000. If we do a small number, so 2.54 times 10 to the negative 8. Anytime I see that negative, I know I need to make a small number. So I will take the decimal part and I'll just sort of automatically write it on this side of the paper towards the right side of the paper. So 2.54, because I know that I'm going to need to move my decimal out this way. So how many hops do I have to take? I have to take 8 hops. The first hop is always going to be to get over that number. So that drops me down to now 7 more hops. So I know that I have to put 7 zeros in front of it. 1, 2, 3, 4, 5, 6, and 7. And now the decimal will sit there. Always ask yourself, does this make sense with what I initially had? So I initially had something that was talking about something tiny, and this looks tiny. So there's the 1, 2, 3, 4, 5, 6, 7, and 8. So I'll give you just 2 of these. Write out 3.04 times 10 to the 2 and 1.1 times 10 to the negative 18. I'll give you, for that, I'm just going to give you guys like a minute and a half. Okay, so sometimes the number is so small that you can kind of almost do the hops like right here and see, okay, I've got to move the decimal over 2 places to make it larger. So my final value is 304. Sometimes you don't even really have to do the hops. You can kind of just do it in your head. Then you have something like this, which is so icky, right? Who wants to write that whole thing out? I made you do it so that you could be happy about scientific notation in some instances, because nobody wants to write this number out over and over. So let's put it over here, 1.1. I get to move it, that first hop, that drops my hops down to 17, right? We were at 18, that's 17. So I have to put 17 zeros in. Okay, 1, 2, 3, 4. Okay, so it looks something like that. I don't even know if there's actually 17 zeros. I might have missed one there, but we're going to infer that there's 17 zeros. So yeah, if you were to write something out like that for an instructor on exam, that would be a total pain. We would much rather see this. And this sort of loses meaning, right? If we had 1.1 times 10 to the negative 18 and 1.1 times 10 to the negative 17, they're going to look almost they almost are identical looking in the zero quantities. So sorry, 17. So when you write them out like this, they kind of lose their meaning. But when I see it here, I can see, oh, this is to the negative 18. This is to the negative 17. This is a larger number. This is a smaller number. Here, you'd have to like manually count everything out. That's a pain. So scientific notation will follow us for the whole semester. This we kind of talked about in the beginning. Reported scientific numbers. So the numbers on the left side are what are called certain values. We know for sure, like our piece of equipment measured that, and it was exactly a 4 in the tens place, a 5 in the ones place, an 8 in the tenths place, a 7 in the hundredths place. Now the value all the way over to the right is always going to be your estimated value. Sometimes that estimation is something that you're doing as a scientist or as a student looking at a ruler. You're measuring between tick marks and you're guesstimating between the tick marks. Your scales and equipment also do this as well. They just do it automatically. So when you go to stand on a scale and you're at 140.5 pounds, it's estimating that 0.5 for you. You're somewhere between 140.4 and 140.6. The more certain numbers you have, the more precise your number gets, or the more what we call significant figures a number has, the more precise a number has. So have you guys heard of significant figures before? We've taken like physics and things like that. So significant figures are numbers that tell us something about the precision of the number. So let's look at this here. We have this blue material. It's probably like copper 2 sulfate. And we put it on a scale. And this is kind of a crappy scale. So it just has tick marks at the every 1 gram. Okay, so I know for sure when looking at this that we've surpassed the 1 gram. We haven't quite gotten to the 2 gram point. So I know that we're going to put the 1 there. And then I can estimate how far between the 1 and the 2 I am. And in this case, they estimated that it was like 2/10 of the way there. So the 1 is certain. The 2 is our guesstimation between the ticks, 1.2 grams. This number we would say has 2 significant figures, 2 levels of precision. What if we have a more precise scale? So this scale, instead of having ticks at every 1 gram, they have ticks at every 1/10 of a gram. So now I've got this cute little pistachio over here, and he is measuring past 1 gram. He definitely hasn't gone to 2 grams, so he's past 1 gram. And we can actually even go into the tick marks and see that he sits between the first, the second and the third tick mark. All right, so we know for sure he's surpassed the second tick mark on the 10th place. We can estimate between the 0.2 and the 0.3, in this case, the person who observed this, said it was a little closer to the 0.3, so they gave it a value of 6. It was sort of in the middle, but closer to the 0.3. So this number, this value is 1.26. The 6 would be the estimated value. This number has 1, 2, 3 levels of precision, or 3 significant figures. This is a more precise number than that last number we were looking at. So how do we classify a number as being a significant figure? How do I know that it's talking about precision? Well, the first rule is super easy. If you have a number and it is a non-zero number, all non-zeros digits are significant. So that one's pretty easy. So if I write like 4115, okay, 4,115. This value has 4 significant figures, 4 sig figs. Okay, 4 levels of precision. Let's say I had a number like this, 432. This number only has 3 sig figs. Okay, this has more significance than this does. Where it gets tricky with significant figures is zeros. Some zeros are significant and some zeros are not. So we just kind of got to follow these rules. The first thing is interior zeros, or anytime you have zeros that are between 2 non-zero numbers, those are always considered significant. Okay, so if I write a number like this, 51004. Well, based off of rule 1, we know that the 5 is significant. We know the 1 is significant, and we know the 4 is significant. But what are significant figures? It's talking about precision, and a number is going to be precise in a block. We're not going to have like some numbers that are precise, and then all of a sudden the numbers aren't precise or measured, and then all of a sudden they're precise again. It's going to happen in a block. So the 2 zeros here in between these sig figs and these sig figs are also significant. So we can check those off. So this would have 1, 2, 3, 4, and 5 significant figures. So 5 sig figs. This is a nice valued number, right? This has more sig figs than some of those numbers we saw earlier. All right, so trailing zeros to the right of a non-zero number that fall after a decimal place are significant. Again, trailing zeros, trailing meaning it comes after the root number or the number that where all the like values are. If you have those falling after a decimal place, they're significant. So let me go over to the whiteboard and show you the same number. I'm gonna write the same number in just a few different ways. So 4, like that. And then I'm gonna write it as 4.00. I'm gonna write it like this, 4.0000. Okay? So they're all talking about 4, but they're talking about 4 at different levels of precision. This is sort of loosey-goosey. It's like, oh yeah, you know, I don't know, it's like 4 pounds. Okay, so this thing only has 1 significant figure. This was measured on a scale that was more precise out to the hundreds place. So this is saying, no, it's not just loosey-goosey 4, it's 4 to the hundredths place. So we would say that this has 3 sig figs. The 4 is significant and the 2 zeros after it are also significant. So 3 sig figs. Scientists are lazy. They're some of the laziest people I know. So they're not going to write zeros if they don't have to. All right. If they're writing zeros, it's because their equipment is good enough to get the measurement out to that value. This guy down here is not just, again, saying, oh, it's 4 pounds. It's saying, no, it's exactly 4 pounds out to 4 decimal places. So we want to preserve all of that. So this thing has 1, 2, 3, 4, and 5 sig figs. Okay. Let's say I have a number like this, 0.1400. This 1 is significant, this 4 is significant, and these 2 zeros are also significant. So even if the root number comes after the decimal as well, the zeros that come after it are also significant. So we would say this thing has 4 sig figs. I think the next rule is going to talk specifically about this 0. So why is that 0? Why didn't I count that 0? See what our next rule is. Oh, no, we've got this one. Okay, trailing 0, we'll come back to that, but trailing zeros that fall before a decimal point are significant. So if you have zeros that fall before a decimal point that is specifically explicitly written, we would include those. So let's say we have 100.00. The 1 is obviously significant, that's easy. These zeros are significant here because they're coming after the decimal place, after the non-zero number. And then these 2 zeros here are significant because they're becoming before a decimal, okay, after the root number. So we include those. So this thing would have 1, 2, 3, 4, 5 sig figs. Another way too that I would determine that these are significant is because I can't have this be significant over here and these be significant and then those 2 in the center not be. It happens in a chunk. Now the next rule is talking about leading zeros. So leading zeros, zeros to the left of the first non-zero number are never significant. Okay, they only serve to help us figure out where the decimal place is. Again, zeros that are in front of, because we read left to right, right? So the zeros that are to the left of or in front of your number are just acting as a placeholder. They don't tell me anything about precision. If I write this here, so 0.000031. Where does the actual number start? Like, where does the precision start? It starts here with that first non-zero number. These zeros in front are just preserving or holding how small the number is. So the 3 is significant, the 1 is significant. Those are not telling us about precision. How do you make a number more precise? You start to tag things on to the right side of it. You don't tag things on to the left side of it. Okay, precision happens as we move in this direction. So don't include those zeros that sit in the front. That is why when I had that previous, when I had this number here, the 0.1400, I didn't include this 0 because it's sitting in front of the number. Okay, it's just helping us to decide where the decimal is. So let's say we have 0.003010. Lots of zeros. All right, I always start when I'm trying to figure out how many sig figs there are, I start with the non-zero numbers because those are easy to determine. So I know this 3 is significant. I know this 1 has to be significant. Then I look for any interior zeros, so that has to be significant. Now we're stuck with what do we do with these and what do we do with this? Well, leading zeros, zeros in front of your root number, those are just placeholders. That doesn't tell me anything about significance. Zeros that come after the number, that are also after the decimal, oh yeah, we're going to say that's significant. So this thing would have 4 sig figs or 4 levels of precision. The last rule, it's not even really a rule, it's sort of just telling you don't do this. Trailing zeros at the end of a number, but before an implied decimal point, are ambiguous and should be avoided at all costs. All right, so let's look at this number here. Clear this out. Okay, if I go 100 or 1,100,000 and I write it like this versus writing it like this. And then I put a decimal here. They look the same, but they have a different number of significant figures. This thing down here, because that decimal place was actually written in, what it's saying is that all of these zeros are significant. They have something to do with the precision. So this isn't just 1,100,000. It's like exactly 1,100,000 to the ones place. So this thing has 7 sig figs. All right, what about this thing up here? Well, this is more loosey-goosey. I know the 1 is significant and I know this 1 is significant. These zeros, are they significant? I don't know. I don't know. I can't tell the way that it's written if those are like, is this precise to the thousands place or the ones place? I don't know. So we could say that this is ambiguous. Or we know for sure there are 2 sig figs. So we could say it has 2 sig figs. If we were to run a calculation using this number, we would only be able to use 2 significant figures. So let's say we have, 8 billion. If it's written like this thing has 1 sig fig. Okay, it's not a very precise piece of information. Now, what if like you're trying to write a number and you're trying to relay to the reader that, well, it's not just like the 8 that's significant. A couple of my zeros are significant too. Let's say that the 8 is significant and 4 of the zeros are significant. How can I work around this? Because I can't put the decimal there, right? I can't put it there because this would mean that these are significant and that's not true. And putting the decimal here would mean that it's a smaller number that it actually is. So your workaround is to write this thing in scientific notation. So if I take this and I turn it into 8.0000, well, then you can see that I have 1, 2, 3, 4, 5 significant figures, and then I can preserve its size by adding my exponent, 10 to the 9th. So that's a workaround if you want to show that some of the zeros are significant and the other ones aren't. Questions so far on significant figures? This first test, there's a lot of talk of significant figures. My care for significant figures decreases dramatically after the first test, okay? Because they're kind of a pain. I mean, you should always keep sig figs in mind. We don't want to, underestimate the precision of a number, but I stopped caring quite as much. Let's look at a couple examples that they have in the slides. I do think I gotta change this out. Sometimes these are the slides from the text, and sometimes they are not correct. So yeah, let's look here. Yeah, I need to add a 0 there. Okay, cool. So we'll come back to that in a second. One thing I do want to talk about actually is identifying what's known as an exact number. So all this stuff on significant figures, this whole thing, relates to measured numbers, right? You can get better at measuring something if you have a more precise ruler or you have a better scale or more sensitive scale. When you're dealing with exact numbers, there are no significant figures. It's like an unlimited number of sig figs. There's no like lack of precision. So things that are classified as exact numbers, like when you count a discrete object, okay? If I count the eggs in a dozen or a carton of eggs, there's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm not going to get better at counting those. There's no like increased precision or decreased precision. It just is what it is. Same thing with like integral numbers that are part of an equation. Those are unlimited sig figs. And then these things called conversion factors or defined quantities, when two things equal each other. For you guys, most of the conversion factors you're going to be working with in class, we're just going to assume have an unlimited number of sig figs. So do you see how 1 inch is equal to 2.54 centimeters? This isn't 1 sig fig and this 3 sig figs. They're both unlimited sig figs. So yeah, we'll stay here. So 1 inch is equivalent or equal to 2.54 centimeters. Really, that's like saying 1.00000, and those zeros go out like all the way to infinity. Okay, it's like the most precise one you could ever come across. 1 inch is equal to or equivalent to 2.54, and again, 0, 0, 0, with those zeros extending all the way out to infinity, because it's like the most precise 2.54 you can ever get. You're not going to get more precise than these two. So just know that when we're using conversion factors, for the most part, those things have an unlimited number of sig figs. Let's go back over here. So looking at, go away whiteboard. Okay. How many significant figures are in each of these numbers? So for this first one, we have 0.0035. This is 2 significant figures. Why are the zeros in front not classified as being significant? I want to be able to write on here. So these zeros are not significant because they're in front of the root number, right? So always kind of find, where is my first non-zero number? That's the start of the number. If there's zeros in front, they're just placeholders. So the 3 and the 5 give us the 2. This one here, okay, what's the first non-zero number? That's the start of the number. I know the 1 is significant. I know that 8 is significant. Well, zeros in the middle have to be significant. And then this 0 at the end is also significant. Why? Because it's coming after the base number and after a decimal place. Wouldn't write it in if it didn't tell me something about how precise it is. So 4 sig figs. This one here is pretty easy. 4 sig figs. Why? Because they're all non-zero. This one here is incorrect in the slides. That's why I added a 0. So it said 3 sig figs with 2.9. That's not okay. So 3 sig figs would have to be 2.9 with a 0. We would need another digit in there. So if you want to make a note, just so you don't mess up if you're reviewing on the slides. Here, 1 dozen equals 12. That's not up for debate. You're not going to get a better relationship by having a better ruler or whatever, a scale, whatever it happens to be. I mean, they're discrete objects, so that's just the definition. This thing here, this has 5 significant figures. So the 1 is significant. This is the start of the number. These zeros over here are coming after the decimal, after the number, and then these zeros in the middle would also be significant. They're coming before a decimal, after the number. This guy here, ambiguous. How many significant figures do I know I have for sure? I know I have 1. I don't know about the zeros. I can't tell the way that it's written. So is it 100,000 grams, like loosey-goosey, or is it like a really precise 100,000 grams? I don't know. I can't tell. So let me have you guys do a couple things with sig figs. We'll come back to rules of rounding. Grab something. Okay, so here's a worksheet. This is, if you want to revisit this worksheet later, it is in Moodle underneath measurements worksheets in the chapter 1-2 section. So you can pull it up there. Okay, so indicate how many significant figures are in each of the following values. So I'm going to give you guys about like 4 to 5 minutes for you to do as many of them as you can. Okay, so start in the first column, work your way down, and then just continue on. If you don't get through all of them, it's okay. If you want to, in addition to doing that, you may want to write yourself some notes on why certain zeros are and aren't significant, just so you can remember at a later point. And I will see you guys back in about 5 minutes. All right, so going through these, all non-zero, all significant. So we'll take 5 for that one. This one here, all the non-zeros are significant, and then this 0 is sitting in between, so it's also significant. So we've got what, 3 here and another 3 here for a total of 6 sig figs. This one here, I know the 1 significant and I know the 3 significant, and that just defaults to the things in the middle have to be significant. So 4 for this. This, what's the first non-zero number? It's this. So this is where the number starts. Significant, significant, significant. This 0 is not significant. It is in front of your first non-zero number. It's a leading 0. It's just a placeholder. So only 3 sig figs for that. This one here, significant, significant, and then we've got internal zeros that are significant for. This one's got a combination of a couple things. So let's find the first non-zero number. It's this 3 here. That's where the number starts. All right, that's significant. The 4 is significant. This 0 here is a trailing 0. It comes after the number, after the decimal. That's also significant. These zeros, just like this 0 over here, is to the left of the number. It's just a placeholder. So it's not that we don't write the number, it just isn't a significant figure. It just is not telling us how precise anything is. So 3 sig figs. This guy here, bam, 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 bam. All those are significant, 5. Only 1 sig fig for this thing, okay? All those leading zeros, just placeholders. This one, ambiguous. How many sig figs could I use / honor? 1, okay? This one here, all those are significant, 6. This guy, all those are significant. So what, 4, 5, 5. Why did the person write these zeros? Because they like writing zeros? No, they wrote it because they wanted you to know that this is like a very precise one. This last one, all significant. So 1, 2, 3, 4, 5, 6, 6 sig figs. So you guys feeling okay with identifying significant figures? I'm seeing some yeses. Excuse me. The Master in Chemistry will give you a bunch of practice with this. Hold on. Turkey. It's okay. Sorry. That's my French bulldog's name, Turkey. He will be joining us for the semester. Okay. So you guys remember when you would round things back in the day? And if it was 4, what was it? If it was 4 or under, the number stays. If it was 5 or greater, you rounded up. Pull up the slides here. Oh, hello, annotations. So when rounding in a calculation, the resulting data needs to reflect the correct number of sig figs. For calculation involving multiple steps, remember you only want to round at the very end. So you don't want to round in intermittent steps because you can get a rounding error. So when rounding, use only the last or leftmost digit being dropped to decide which direction to round. Ignore all other digits to the right. I'll show you an example of what that means. Round down if the last digit dropped is 4 or less. Round up if the last digit dropped is 5 or more. So I'm going to write a number that's pretty similar. 4.4 and then 4.5. Both of these numbers currently they have 2 significant figures, right? This and this, this and this. Well, what if I couldn't have 2 sig figs? What if I have to round this thing to 1 sig fig? How I do that is I start with the leftmost non-zero number. That's going to be the number I get to keep. Everything else has to get dropped, okay? So I'm going to cut everything else off. Now I look at the number that's the leftmost number getting dropped, and that tells me what to do with the number I'm keeping as far as do I round up or down. So for this first one, the 4 tells the 4 to stay, right? So if I take 4.4 and I round it to 1 sig fig, it would round to 4. What if I have 4.5? Okay, it's only a 1/10 difference, but that's the cutoff point where we go up instead of down. So here I want to have 1 sig fig, so I want to keep the 4. I drop everything else. Well, what does the 5 tell the 4 to do? It tells it to round up. So this thing rounds up to 5. Okay, so 4.4 rounds to 4, 4.5 rounds to 5. Do you guys remember doing that like long time ago? Okay. Let's write a number, this sort of number slightly different. So let's say it's 4.45. How many sig figs is this? This is 3 sig figs, the way it's written right now. And let's say again, I wanna make this 1 sig fig. All right, well, I find the number to the left that I'm gonna keep. So I'm gonna keep the 4. Everything else gets dropped off. Okay. Now you only look at the number that's sitting right next to the numbers that you're keeping. We only look at the 4. What does the 4 tell this 4 to do? It tells it to stay. So this would be rounded to 4. Why I use this as an example is because quite often, I'll write it in red, students will play this game, 4.45, and they'll go, well, doesn't the 5 tell the 4 to round up to a 5? And then the 5 tells that 4 to round up to a 5? No, we don't want to do that. Because what if you have a number like this, 4.444445? Like how far back do you have to go? Does this 5 tell this to go up? That tells this that no, we just look at whatever the number is that comes. That's the first number being dropped. If I have a number that is larger, so let's say I have like 21,482. This number, the way it's written right now, has 5 significant figures. Okay. Let's say I want to round this to 2 significant figures. So look at your number, find the numbers that you're going to keep. So I'm going to keep the 2 and I'm going to keep the 1, and everything else is, it's not that the magnitude drops, but the significant drops. So we're going to get rid of those. We look at the 4. We don't look at the 8 to round the 4 to a 5. We just look at the 4. What does the 4 tell the 1 to do? It tells it to stay a 1. So we're going to have a 2. We're going to have a 1. But 21,482 does not round to 21. So in those places there, we need to fill them in with zeros. So 21,482 rounds to 21,000. Right? We need to keep that 1,000 magnitude. We don't want to take 21,482 and say it just rounds to 21. We have to preserve the size of it. So I want you to try one of these. Let's say we have 4,352,111. This is 7 sig figs. I want you to round it to, let's round it to 3 significant figures, 3 sig figs. Okay, so originally we had 7 sig figs, so the number was looking pretty precise, but let's say we can't actually be that precise. We only get to have 3 significant figures. So I'm going to go to the leftmost non-zero number. I keep the 4, I keep the 3, and I keep the 5. Everything else, the significance is going to drop, not its placeholder, but the significance. So the 2 tells the 5 to stay its course. So we're going to keep the 4, the 3, and the 5. All the other spots need to get filled in with zeros. Okay, because again, we want to preserve the size of the number. We just want to change its precision. This is a very precise number. This is not as precise of a number, but they're still talking about the same sized number, right? This is 4,352,111. This is 4,350,000. We rounded it to something that's less precise. Why would you ever have to round something to a less precise number? Have you guys ever taken two numbers and divided it in your calculator, and then you get this like long trail of decimals, and you're like, how many of these am I supposed to use? Like, what do they want from me? Well, when they're measured values, there's actually a set of rules. So if those numbers were, you know, the height of a box times the width of a box or something like that, the resulting number will actually follow a system. And let's look at what that is. It looks like I've got. Someone said, I know originally you said to avoid ambiguous numbers. Is this still counting as ambiguous even though there's 3 sig figs? Yeah, so this thing is ambiguous, but I know that there's a minimum of 3 sig figs. So we're kind of honoring it. You could write it in scientific notation as 3.5 times 10 to the what, 1, 2, 3, 4, 5, 6, 6 power. But really, if I'm looking at this number, I'm just going to honor those 3 sig figs. So we're good writing it that way. Okay. So we've got the rules of rounding down. So let's talk about when we're running calculations. I would say 95% of the calculations you guys are going to do in class are really going to be multiplication division. So this is the rule that you really want to get down. When you're taking, and multiplication division are the opposite in order of operations, but they have the same level of importance, just like addition and subtraction are opposite, but they're at the same priority level. So multiplication and division follow the same rule. And what it says is the result of either a multiplication or division problem will always carry the same number of significant figures as the factor with the fewest significant figures. So you are only as precise, your calculation is only as precise as the least precise piece of information. So let's look at an example here. I have 3 numbers that I'm going to multiply together. I've got 5.02. This has 3 significant figures. This is an okay number. This 89.665 is a really precise piece of information. It has 5 significant figures. This last number, 0.10, this is a crappy piece of information. It's 2 sig figs, right? You have this like super expensive scale and then you use like your kid's ruler. Okay, so you didn't get a very precise piece of information. So your final answer is going to be crappy. It can only be as good as your least precise piece of information. So when you plug this into your calculator, you end up with this number with this long stream of decimals. How many do you get to use? You only get to use 2 of them. All right, we get to keep the 4 and the 5. Everything else gets dropped. The same thing is going to be true for division. And I feel like when we divide numbers too, that is when we especially start to see these really long decimal numbers. So if I have 5.892 and I divide it by 6.10, all right, first number has 4 sig figs, second number has 3 sig figs. Calculator gives us this huge number. What do we get to do? We can only keep 3 significant figures. So go to your first non-zero number. Remember, this isn't significant, it's just a placeholder. We get to keep the 9, we get to keep the 6, and we get to keep the 5. Everything else gets dropped. The 9 tells the 5, go up to a 6. And that's why we have that 0.966. So you're only as precise as your least precise piece of information when you're running multiplication division. This can at times drive some of my students crazy because they're like, oh my gosh, look at how precise my number is. And I have to get rid of all of that. Yeah, because all of this is really just junk information. It's not saying anything of any value. So let's take, I'm going to have you do this. So make sure you have your calculator, and where did mine go? I'll find it in a second. Let's say we have 12,000, and we're going to divide that by 3.4621. I want you to plug it into your calculator, get an answer, and then round it to the correct number of sig figs using that rule you just learned. I'll give you a minute and a half for it. Minute. Okay, and I have been known in the past to mess up a calculation here or there. So if you're looking at it and you're like, that doesn't look right, I think she's wrong, I could very well be wrong. So I'm going to double check this 3.4621. Only when I make up these problems on the fly. Okay, so our final answer is 3,466.10439. We got all these decimals, right? How many sig figs do we get to honor? Two sig figs. This thing here, it's ambiguous, but I know for sure it has 2 sig figs. This thing here is really nice. 1, 2, 3, 4, 5, 5 levels of precision, but it doesn't matter. The 2 wins out. So we are going to keep the 3 and we're going to keep the 4. So 3, sorry, we'll cut everything else off. The 6 tells the 4 to round up. So 3, 5. And then I have to fill zeros in with those 2 spots because 3,466 would round up to 3,500. Right. Sometimes you may have to add some significance. So let's say we have 6.0000, and we're going to divide it by 3.00. All right. You don't even have to really plug it in your calculator. 6 divided by 3 is going to give you what? It's going to give you a value of 2, and your calculator is going to spit out just a 2. Well, how many significant figures does the numerator here have? 1, 2, 3, 4, 5 sig figs. How many does the denominator have? It has 3 sig figs. Your resulting answer needs to have this many sig figs. How many does it have right now? 1. A sad single sig fig. So how do we give it 2 more significant figures? Well, we put a decimal and then we add 2 zeros at the end. Okay, if we write 2 like this, it's 1 sig fig. If we write 2 like this with those additional, that's 2 sig figs. Sorry, 3 sig figs. So sometimes you may have to tack a 0 on to get you to the correct number of significant figures. That you don't see quite as often, but just so you know. Let's round a couple things and pull that worksheet back up. And we're just going to lecture through. We've got this and then one more rule, and then we're going to stop there because I want to keep you guys on the same schedule as my in-person class, just in case they have to move online or something like that. And it just makes it a little less confusing for me. Okay, so looking at this, I want you to do A. Come on, I want to annotate. You're not going to let me do it. Oh, I got a comment in here. Does this apply to calculating temperature like in lab 1 when you're multiplying, dividing as well as adding? Joan, addition, subtraction follows a different set of rules, and I'll show you that after we've gone through multiplication, division. Okay, cool. Where are you, worksheet? Why are you giving me a hard time? Okay, hold on. I'm gonna... Stop share. Try and reshare. So let's do A. Let's do C. And let's do G. All right, the two on the left are multiplication problems. The one on the right is a division problem. They'll follow the same rule though. So I'll give you 2 minutes for that. Okay, so for this one, we end up getting a number of what, 90.06. This has 3 sig figs, this has 2 sig figs, so we keep 2 of them. So I'm going to keep the 9 and I'm going to keep the 0. And I'm going to actually write it like this. I'm going to put the decimal right there. When I write that decimal in, it just lets who's ever reading that number at a later date know, oh, yes, she's precise to the ones place. This next one here, we've got what, 81.04 times 0.010. And I get 0.8104. How many significant figures? Well, this has 4 sig figs. This has 2 sig figs. Okay, the 1 and the 0 are significant. So again, we're going to round to 2 sig figs. I keep the 8 and I keep the 1. Everything else gets dropped, so 0.81. The 0 that's sitting there in the front, again, is just to help read the decimal, where the decimal place is. It's not necessary. If you wrote it as 0.81, that's fine as well. Okay, either way. Over here on the division side, we've got 28 0.367, and we're going to divide it by 3.74. And again, yeah, I said with division, that's where we get those like really, really long numbers. So 7.5847596. Most of this is junk information. This is pretty precise, 5. This is less precise, 3. So we get to honor 3. Okay, so I get to keep the 7, the 5, and the 8. Everything else gets cut off. The 4 tells the 8 to stay its course. So 7.58, and we are done. So how is that for you concept-wise? Okay. You're going to do so much practice with this throughout the semester just by running calculations that we're going to be rounding to sig figs quite often. If there's any specific questions though, anything you're like, oh, I don't really get this, or what's happening there, you can throw it in the chat. Before we go, I do want to visit the rules for addition and subtraction, which are different than multiplication division. Okay, so if we're dealing with addition and subtraction, which happens from time to time, in addition subtraction calculations, the result carries the same number of decimal places as the quantity carrying the fewest decimal places. So don't use significant figures to round for addition subtraction. Kind of don't even think about the word significant figure, concept of significant figure when you're doing addition subtraction. And instead, go off of the decimal places. So let's look at this here where we're adding 3 numbers. And you might remember from like grammar school when you used to add numbers and you'd line up the decimals on top of each other because it kind of made it easier to add and subtract. So you may want to do it when you're working with this as well. This makes it very clear which one has the lowest decimal place, right? Here, this number here only has 2 decimal places. This one has 3, and this one also has 3. So I'm going to add them up like I normally would. My calculator is going to pop out a number, but because this has 2 decimal places, I need to round this to 2 decimal places. All right, so it becomes 9.21. Now, this number has 3 sig figs, and I know the final also has 3 sig figs. That's just coincidental. That does not always happen. That's not always the case. Okay, we can actually look at the problem on the next page, where let's say I've got these 2 numbers and I'm going to subtract them from each other. So 4.8 minus 3.965. This first number only has 1 decimal place. The bottom one has 3 decimal places. So when I subtract them out, I end up getting 3 decimal places, but I only get to use a single decimal place. So I'm going to drop the 3 and the 5. The 3 tells the 8 to stay its course, so 0.8. You'll notice this thing had 2 sig figs, this thing had 4 sig figs. Our final answer has 1 sig figs because sig figs don't matter when we're talking about addition subtraction. All right. Try not to get those rules mixed up. Addition, subtraction, you're not going to see a crazy amount. Okay. Know that if you have multiple steps, round at the end. All right. If you have addition, subtraction, and multiplication, division, run the functions, don't round to the end. All right. Let me go through this really quick. And then we'll call it a day. So I know I said I was going to be done after that, but one more thing. All right. In most sciences, we don't use the British system. Okay. Feet, inches, pounds, whatever. It's a hot mess of units. Okay. You may be familiar with it. It may feel familiar, but you're probably not very good at it. How many inches are in a foot? Probably can answer that 12, right? How many feet are in a yard? 3. Okay, how many feet are in a mile? That's when people start to fall apart, right? 5,280. How many inches are in a mile? Who knows? Because the system doesn't have any consistent base unit. Now, the metric system, which is what everyone else uses, is superior. You may not be familiar with it yet, but it is a better system, and I recommend that you learn it, and you have to for the class. But in the metric system, everything has a base 10 to it. It's a unit base 10 system. So let's say I'm looking at a meter, and a meter is roughly a yard. So think of a meter as about 3 feet. If I take a meter and I want to convert it to centimeters, there's 100 centimeters in a meter. If I want to convert it into millimeters, there's 1,000 millimeters in a meter. It's all a factor of 10, 100, 1,000, 10,000. How many meters are in, let's say, a decameter? 10 meters in a decameter. How many meters in a hectometer? 100 meters in a hectometer. How many meters in a kilometer? 1,000 meters in a kilometer. We add or subtract zeros, meaning we can move between units just by moving the decimal around. And I'll show you guys how to do that next week, but it is just a better system. The metric system, it has the base unit of meter, gram, second, and degrees Celsius. The international system of units, which is what they use mostly in the science field. Sometimes it's referred to as the SI units. Those are based off the metric system. They're slightly different. The length is still a meter. Mass, their base unit is a kilogram instead of using a gram, because a gram's kind of too small. So they go with kilogram. If you're wondering, I have no idea how much a kilogram even is. It's about 2.2 pounds. Okay, so something you could hold in your hand. Time is in seconds, and temperature is in this thing called Kelvin, which is more directly related to degrees Celsius than it is with Fahrenheit. It doesn't really have anything to do with Fahrenheit. So no need to worry about that. The last thing here, what is the difference between weight and mass? So pounds, like when you get on your scale and it gives you a measurement of pounds, that is a weight value. Grams, kilograms, those are mass values. The mass of an object is the measurement of actually how much matter is in it. What's the quantity of actual stuff? Weight, on the other hand, like pounds, that is a measure of the gravitational pull on matter. Now, because we all live on Earth and the gravitational force is consistent here, we can kind of use those interchangeably, right? Weight and mass can be used interchangeably. If you have more mass, if you have more material, you will weigh more because there's more gravitational pull. Now, where this weight mass thing differs is if you leave the pull of gravity. So if you're in space or if you're on another planet or like the moon, your weight will change. Your mass will stay the same though, right? Your mass is your mass is your mass. Your weight is based off of the gravity of the object you're next to. Okay, so we'll leave it there. We're going to do these SI prefixes next time. We're going to get into how awesome the metric system is. You guys are going to love the metric system by the end of this class. So yeah, no class on Monday. Feel free to stay around if you want to chat after this. The intro video, if you weren't here on Monday, there is an intro video that you can look up on the YouTube channel under our playlist. Otherwise, yeah, I'll see you guys next time. Stay around if you have any personal questions. Have a nice weekend. It's supposed to snow quite a bit, so get out there and go sledding. All right, bye guys and gals. I use guys for everyone, so have a good weekend, Meg.